Hi, I'm Royson from Samsung AI Cambridge, and my goal today is to give an overview of our work on how we go about deploying super resolution on the mobile, which is recently made feasible and practical because of the powerful mobile processors that we have today. So what is super resolution? Super resolution is a task that entails the upsampling of a low-resolution image to a high-resolution image. And it's a task that is parked under a general umbrella of image restoration tasks in computer vision. Today, solutions to this problem are dominated by the use of neural networks because they produce visually appealing results as compared to traditional approaches back in the day. So why then stream at really high resolutions, as you know from the last. Now, super resolution not only could upscale any image to fit your experience, but more importantly, our team believes to save data on top of standard compression techniques. Instagram or Facebook or LinkedIn or Twitter feed without super resolution. And this applies to any form of media feed, whether you're looking at photos of your favorite cats, literally any app that delivers images. But the point is having super resolution running on my device. It's important to run it on the device. Why not offload computation? To be really expensive, and depending on your application, more importantly, it fundamentally contradicts the application of super resolution as a means of image and offload the image or part of the more data. So what? Just run it. This model multiply add operations. And on the x-axis, AK. And the bigger the upsample, the good news is that some of the popular ones, and they're up to like 2K, which is the red line, is still really expensive. Image classification mobile models like your super resolution mobile models are orders of magnitude. And the reason for this is because these models are upscaling models, or they tend to get larger and larger. This challenge. We allocate them to the mobile SoCs, which in this would then generate two models. I'll explain how later. We put the bigger model in the CPU and GPU, and we put which would decide whether each patch is hard or easy to upscale. The patches would then be allocated to the relevant compute engines, and the upsample patches will stitch back again, to get the upsample image. So one of the key ideas here is how we design the scheduling, which we call difficulty-aware scheduling. And the way we determine whether a image patch is easy or hard to upscale is by using the total variation. So given image patch P, the total variation is simply the sum of difference between each adjacent pixel in an image. In other words, it measures how smooth an image is. By estimating the upsampling difficulty of each image patch, we are able to find two interesting key observations. One of which is the higher the TV of the low resolution image, the harder it is to upscale. So on the y-axis here, you have the PSNR of the upsample image using one of our models. And the x-axis here is the total variation of the low-resolution image. And you could see that the lower the TV of the low-resolution image, the closer the upsampled image would be to the ground truth. The second interesting observation is that given two different models of different compute, we found that hard patches are similarly hard for both models. So the difference in this plot compared to the previous one is that the y-axis now is the difference in PSNR from upscaling using the large and the compact model. In other words, it measures how well the large model performs as compared to the compact model. To show you how it looks like visually, we take two extreme points. We take the easy to upscale image and we schedule it to the large model. And we take the large image, the hard image, and we schedule it to the more compact model. Now this is counterintuitive, but I want to re-emphasize that if an image is hard to upscale, the accuracy difference between using the large and compact model is similar. Therefore, we can save computation by just scheduling the hard patches to the compact model. Now, how does our framework know whether an image is easy enough to be scheduled to the larger model? The framework automatically tunes the TV threshold, which is the red line on the plot. And it does that by first taking a SuperResolution model. We apply a bunch of compression techniques on it to generate a set of model variants, compressed model variants. We validate it and take its PSNR, and we run it on the device on each compute engine. We then take the parental optimal compressed models, which looks like this. So on the y-axis, you have the PSNR, and on the x-axis, you have the time it takes to run on the DSP. And we do this for each compute engine. And each point represents a different compressed model, and we just take the parental front. Lastly, we tune the TV threshold, and we select two models to be mapped to the device. In this case, we're using the Qualcomm Snapdragon 845. And this depends on the user max error threshold, which I will explain more later. So for evaluation, we're comparing between fitting a baseline model using our framework on the target platform, which has the CPU, GPU, and DSP, versus just running it on the GPU, which is the most widely used deployment for most deep learning frameworks today. On the y-axis here, we have the parental optimal pairs that is chosen by our framework. And on the x-axis, we have the speed up. The numbers on the bars are the error drops. So all the user has to do is to select an error tolerance, and our framework will map the appropriate parental optimal pair and the TV threshold to find the appropriate speed up and accuracy trade-off. So for example, if the user says that he does not want any error drop, then our framework could propose two model pairs that would have around a 40% speed up. But if the user could allow a greater error drop, then we could accommodate even more speed ups, up to 4.3. And we not only compare this to the GPU, we also compare it with a baseline just running on the CPU and on the baseline running on both the CPU and GPU. And you can find that in our paper. So just to summarize, we went through how the framework exploits the available compute engines and how it schedules based on the upsampling difficulty of each image. We also show the gains of using our framework through the generation of a two-model processing system. Lastly, the methodology is extensible for any mobile SoC with heterogeneous compute engines. So MobiSR, which is a framework, can be still used to take advantage of newer emerging platforms. So let's say you have an MPU, for instance, then we will expect even larger gains. And that's it. Thanks.